on the quiz preview, okay, we're even going back into special rights and things like that, trying to, work on that stuff. So, when we get into here, remember with the special rights,
oh, Jesus.
When we did the 45, 45, 90s, remember our pattern typically on these, would be x square root of 2. And understanding that's a key here, because then when I see this, I'm like, that's normally x square root of 2.
Everything else is 6.
In this case, right, that tells me my x value is 6. And that tells me what each of my other sides would be. So it makes it pretty easy if I understand that basic principle with these. When I move over a little bit here, though, and squeeze into number 2, when I've got a 30, 60, 90,
short side is x.
yes,
Long side is x root 3. Hypotenuse is 2.
yes. Okay, so that's my base for my special right triangle. But again, look at which side you're given. I'm given the hypotenuse this time. So this is really what 2x is. So I figure out, in this case, my x value would be 4, which is my short side. And then my long leg is just that x value times the square root of 3. There's no way around this. You have to know those specials or this is not going to work. Because I can't just do the Pythagorean theorem on it and try to figure it out because I don't have enough information to do it. Okay. So special rights, definitely something we need to know for this. Additionally, find the value for the following trig functions. Identify what quadrant the terminal side is in, what sign the function should have in that quadrant, then use special right triangles to find the value. Woo.
That's a lot.
Yeah, there's a lot of stuff I got to be doing here. So, all right, cosine of 330. I got to make a 330-degree angle here first. So again, I'm going counterclock. So I'm like, all right, so we got 90, 180, 270. How much more do I need for my angle? 60. So I'm like, all right, I'm just going to approximate here again. So there's my 60. Get this drawn in. Okay. So there's my 330-degree angle. But, all right, let's start answering questions here. Identify what quadrant the terminal side is in.
4.
4. Okay. So we're in quadrant 4. What sign the function should have in that quadrant? All stores take cash. So cosine. Oh, cosine. Should be positive because my terminal side's in the 4th quadrant. Now, if that would have said sine 330, it would have been negative. Okay, so I know that much. Then use special right triangles to find the value. So remember, these are the ones that we twist around to here, and we go, okay, I'm creating a right triangle. If it's 330 to here, what's this angle going to be? Okay, this angle is 30. That's key for me for 2 reasons. One, it lets me figure out this is a 30, 60, 90. And the other thing that's important about that is this is the angle, my 30 here, that I'm going to base my calculation off of. So you're like, oh yeah, it's going with this stuff again. So when I get here, my 30, 60, 90 that I had before, I'm just going to lose the x's. I'm going to consider those to all my x's to be 1s. So here, my short side is 1. My long leg is the square root of 3. Sorry, that's not showing up better, but that's what it is. Square root of 3. And my hypotenuse is 2. So what I'm doing to calculate this again is I'm using this angle, the 30-degree angle. So really, I'm using the cosine of 30. Because again, it's that angle that gets me back to the x-axis that I'm using. So cosine, which sides do I use when I'm doing a cosine? Adjacent over hypotenuse. So square root of 3 over 2. And we're good. If it would have told me that it was supposed to be negative, I'd have to put a negative on here. But it didn't, so I don't. So that's what we are in a fight against. Dealing with all that business. So here again, if we're doing the same thing with b, okay, we're doing the cosecant of 135. So again, got to draw my angle first. So I start rolling around. Okay, there's 90. How much more do I need to get to my terminal side? 45. Okay. Yes, I'm going to be bad. I'm like 45 is right in the middle. I'll sketch this. Okay, so there's my 135. Nice, okay. To finish this, oh, bless you, I right triangle it back to the x-axis. It's always the x-axis we're making that triangle with. And it was, as was already mentioned, to find my reference angle, 135, what's it take to get back to the x-axis? This being 45. Okay, we'll even jumbo. We'll live dangerously. I'm going to let this thing focus again. Which makes this a 45, 45, 90. And if that's the case, I know that my sides are 1 and 1 for my legs, and the square root of 2 for my hypotenuse. So I've got my special right triangle all set up, and now I can start trying to figure out the other information I need. So first, which quadrant's my terminal side in? 2. All right, Q2. What sign should the function have in quadrant 2? Now be careful. All students, what's the inverse of sine? Cosecant. So those are the two functions that are positive in this quadrant. So cosecant still will be positive. Just like in here, in this quadrant, it would be tangent or cotangent. Over here, it would be cosine or secant that would be positive. And if it's in the first quadrant, everything's positive. It's just a great place to be. So once I know that, and I've got my special right, okay, now be careful here. Cosecant. Which sides? Nice, okay? Because sine is opposite over hypotenuse, cosecant's its inverse. So I want hypotenuse over opposite.
Opposite of which one?
The angle that you're using is always the one that's coming off of your reference angle. It's always going to be connected to the x-axis. That will never change. So here, hypotenuse is square root of 2 over opposite, which is 1. And you could just write the square root of 2 if you wanted to, but I just do it because I get used to it. But the biggest thing to remember on this is when you're making your right triangle, it's all about the x-axis. Make your right triangle form with it, and your reference angle is always going to be the angle you're working with. So I really here was working with the cosecant of 45 degrees is what I was doing. Okay? So that's what's up with the specials back here. Then we get to our two favorite parts of all of this. Okay, graphene and identities. So hopefully at this point some of you are starting to see, you know, I really need to put this on my cheat sheet or that on my cheat sheet. Or if some of you haven't been here and you're like, what cheat sheet? The The note cards are back in play, except now you can use both sides. So, yay. All right, so let's see what we got working here. What's this 2 represent in front?
Amplitude.
Amplitude, okay? So if my amplitude equals 2, what that means to me later when I'm calculating stuff is whatever my value normally would be, I'm going to multiply it by 2. And I can kind of keep this stuff straight as I'm working on it. Okay. So then what's this theta over 2? What's going on here? Okay, right. My period...
It's just pi.
Eh, yeah, because remember, 2 cosine theta over 2 is the same thing as 2 cosine 1/2 theta. Okay? So when I have my normal period here of 2 pi, you're dividing it by this number. Dividing it by 1/2, or as what was just mentioned, multiplying by 2. Because dividing by a half, same as multiplying by its inverse. So my period is going to be 4 pi. And you're like, what the heck, Hardy? That's not what your little thing down here does. We'll make an adjustment. Because life is about making adjustments. So I look at this and I'm like, okay, my radian measures. I know I'm always starting with 0. I know as a base, I'm always starting with 0 and then going to whatever my regular period would be here, which in this case is going to be 4 pi. But remember, we're doing quarter points. I know 2 pi is going to be in the middle. It means there would be, after 0, there's going to be 4 more places that I'm putting dots. Well, that's what we've been doing all along. Yeah. What's in between 0 and 2 pi? 1 pi, or pi. And between 2 and 4 is 3 pi. Now, will it always turn out that nice? No, we've learned that, okay? But again, just keep reminding yourself on these that you're just, in this case, dividing by a half or multiplying them by 2. So once I get to the value, then I start looking here and I'm like, okay, normally, if I was just doing cosine and there wasn't an amplitude, normally this would be 1, 0, negative 1, 0, 1. But I have an amplitude change. So I multiply my normal values by 2. So 2, 0, negative 2, 0, 2. And I've got my chart. And if Hardy would have done something smart here, which is what I'm going to do now, I've got to learn to just put blanks on these. That would be so much easier. So I get here and I say, okay, so 2, and I just start plotting. 0, 2, pi is 0, 2 pi is negative 2, 3 pi is 0, 4 pi is 2. Yeah. What's that? Oh, that's okay. Yeah, that's absolutely okay. I can follow. But if you need to change your values on these or feel compelled to do so, that's fine. I won't jump up and down screen. Now, let's swing over here. All right, 5. What's happening this time? What's... Okay, so my amplitude is 2. And then this time, that's dealing with my period. Now that's different than when we had the pi over 2 over there. So my period would be 2 pi divided by my coefficient in front of my theta, which is 2. Which means my period is going to be pi. Now, this is the time that I'm going to talk about what we started to do yesterday some. I know I'm starting with 0. I know I'm ending with pi.
Oh my lord.
Remember, when you're doing these, think about the base and work from that. So for instance, my base normally would look like this. Ben? So what would I do? Well, since I'm dividing by 2, that would be the same as me going through here and multiplying all of these by a half. Because I look at the 2 that I already have, half times 0 would be 0. 1/2 times 2 would be 1 pi. Okay, this makes sense. And now I can visually see where all these values are going to come from. 1 times pi would be pi. 2 times 2 is 4. 1 times pi is pi over 2. 1 times 3 pi is 3 pi over 2 times 2 is 4. And I've already got my pi. Okay? If you need to do some side scratch work or even do it like I'm doing it on here, do that. I know a lot of you do not like taking the time to, but you need to get it right. So once I have that, I can kind of scratch that, get it out of my way. And then I go, okay, my value is being multiplied by 2. My amplitude changed. So normally I'd start at 0, so I'm still going to do that. This would normally be 1, but now it becomes 2, 0, -2, 0. Just took my normal sine values and multiplied them by 2. And once I've done that, I am ready to plot. And this time the graph actually works, because pi over 4 would be this next line. Pi over 2, and back. And if I wanted to keep going, I could. And by you showing me what I've got drawn here, when it says identify the period in quarter points, there are your quarter points by showing me your radians, and identify the period by showing me, you know, well, what did you do? I took 2 pi and divided it by this number. That's sufficient. So whatever you're doing mentally, be like a computer. I want a computer printout of what's going on in your brain. Any issues here on the front so far? Because it kind of, I'm hoping for some of you, this is showing you some stuff you might want to put on that note card as you're doing this. All right, 2 more graphs.
So say like if we do it now like that, can we just put like 0 times 2, 90 times 2, or like 180 divided by 2?
As long as once I see on your graph and in your final part of the chart that it's in radians. Yeah, if you want to start in degrees and transfer back over, that's okay. All right, what's going on in number 6?
Is it the amplitude down through?
No amplitude. There's no number directly in front of sine. Okay, it's just going to be down 3. Now remember, down 3 affects my value, not the radian measures. So here, my period's not changing at all. It's 2 pi. So when I go to chart this, my typical radian values are absolutely positively sufficient because there's no period change, there's no value in front of my theta. But when I do my values, since I'm going down 3, I'm subtracting 3 from all of the typical ones. So again, mental picture. If it was sine, which it is, normally that's 0, 1, 0, -1, 0. But I have to take 3 away from those because I'm shifting it downward. So -3, 1 minus 3 is -2. 0 minus 3 is back to -3. -1 minus 3, -4, and -3. And again, if I do draw these in here, I'm just going to scribble them out at the end, so I don't think about using them. So this time, we're normal again, thank goodness. Pi over 2 is back up to -2. Pi is back to -3. 3 pi over 2 is back to -4. And 2 pi is back to -3. So all we did was take our basic sine curve and shift it down 3 spots. So again, we're not trying to drive you crazy on this. I just did the challenges before to kind of get you thinking a little. All right, one more. Yes. Okay. Here, my theta minus pi means I'm going right pi. This affects my radians. It will not affect my values. Left and right shifts affect your radian measure. So, here's how I would tackle it. Your initial period, well, it still will be, is still 2 pi. So here's the way I would play this. Okay, my typical radian would be 0 pi over 2 pi, 3 pi over 2, 2 pi. But now I'm taking my radian value, and since I'm moving right, I'm adding pi to all of them. I'm adding a full pi to each measure. So 0 would be pi. I'll do the easy ones first. Pi plus pi would be 2 pi. 2 pi plus pi would be 3 pi. Now, if you need to, some of you may be able to look at this and go, well, between 1 and 2 pi, it'd be 1.5 pi, which would be, 3 pi over 2. And in between 2 and 3, well, that'd be 2.5. That'd be 5 halves, or 5 pi over 2. But if that part doesn't work for you, remember, if I'm adding pi to this, there's a couple of things I could do. Worst case scenario, again, I cringe a little bit, but we do what we got to do to make this work. If I had to, I could look at this and say, okay, pi over 2 is the equivalent of 1/2, and I'm adding 1 to it. Okay, it's 3 halves. It's 3 pi over 2. If that's what you need to do to be able to add the fractional parts together, do it. But don't just go, I don't know. If you're looking at 3 halves plus 1 and 5 halves does not immediately pop into your brain, at this point, you need to go this route and get it that way by whatever means necessary. Is our value column changing at all? No. It's cosine. 1, 0, -1, 0, 1. There's what I'm working with. So let's see. So we're starting at pi. We're starting at 1. Okay. At 3 pi over 2, we are down to 0. I'm going to have to stretch this, I know. 2 pi is down to -1. Let me go into stretch mode here. Let me space them out approximately the same here. So 5 pi over 2, we're back to 0. And we're back to 1. Patience is the key in the last two sections. When we're in 14.2 and 14.3, you've got to take the time to do a chart, look at things, and go slow. Okay? And then our favorites of all time. Simplifying and verifying. Now, I still say when we get down to these, I still say simplifying is harder than verifying because you're not quite sure when you're done. But we got this. Now this becomes interesting because you look at this and you're like, okay, sine squared plus cosine squared plus cotangent squared. And your initial thought is to go with sine squared, and you start looking at your identities and you're like, oh, it's 1 minus cosine. But then you start to look at it for a minute and you're like, wait a minute. What's sine squared plus cosine squared equal? 1. And before I go changing cotangent around, wait a minute. Does 1 plus cotangent squared equal anything? Cosecant. Now, could I have gotten there if I changed sine squared and cosine squared into 1 minus their other pieces? Yes, but it would take quite a while to get there. So look at your initial problem to see, is there some sort of identity I can use right away to kind of cut middle pieces out? Now, sometimes there won't be. Tangent over sine. I'm like, yeah, there's not really anything here that's going to help me. So let's see here. What's tangent?
Sine over cosine.
Sine over cosine. And I'm not touching sine. I like sine. Sine likes itself. Do not let fraction divided by fraction get you. Remind yourself, if you need to write it out this way even, do it, okay? If looking at it vertically messes you up, let's look at it horizontally. And then write. When I'm dividing by a fraction, you take its reciprocal and it turns into multiplication. So sine x over cosine x times 1 over sine of x. Awesome. There's no pluses or minuses, so I don't have to worry about being a bond breaker. I wipe those out. Get 1 over cosine, and that's going to be secant. Try to keep going. If you can get it down to one single term, that's usually a pretty good idea that you're done with those. But again, leave sine and cosine alone as much as you can unless there's something for you to be able to simplify. And I'm glad we've got 10 and 11 in here because now we can play the game of not being a bond breaker. All right, verify. In other words, do not touch that, but that's what I'm trying to get to. So I start looking at sine. I'm like, now what normally would get me to sine? 1 over cosecant. So I wonder if we can get there. Let's see. All right, let's see what we got here. What's cosecant going to be? Because I want to turn it into sine. 1 over sine. Okay. Minus, that's kind of important, cosine of x. I'm going to put that over 1 because I'm seeing fractions working here already. Times, what's cotangent? Cosine over sine. Now, before I do anything else, heed the minus.
So those are 2 things for cotangent.
Well, wait, say that again?
Because right here it says 1 over.
Right, but that 1 over tangent I'm very rarely going to use because since I want to get everything into sine and cosine, this is the way to go. I'm even going to put parentheses here because I want to simplify this. Why? Because there's no bonds to worry about breaking. Whatever I can simplify, I'm going to simplify. So I'm just going to remind myself of that by putting my own parentheses in. So here, nothing cancels because I can't cancel side to side, but I would much rather look at one fraction rather than 2. So all I did was multiply straight across. Nothing else I could do with that. But hallelujah, I have a common denominator. Woohoo! So I look at that and I go, okay, let's play that rule again. Let's get to one fraction and see what's going on here. So now I get to a point and I go, okay, I want to get to sine. I'm getting close. Can I turn 1 minus cosine squared into anything? Sine. Because if I look at my identities that I had, and I made my adjustments here, oh yeah, 1 minus cosine squared is sine squared. Okay. So I have sine squared x over the sine of x, and we treat it just like we would exponent rules. If I have like x squared over x, I end up with just the x, or sine of x. I'm done. Woo! So again, patience is your biggest virtue with these. And for some of you, that's a tricky thing. All right. You need to put it on anything up there, you need to put on your cheat sheet.
So you can do this whole, put this whole quiz for you.
If you wanted to.
Which one's the best?
Whatever you want to do. I always tell people, most of the time the people that put a ton of stuff on a note card or something, one of two things happens. Either they don't end up using it because they memorized it all as they were writing it, or they get so confused because they put so much junk on it that they get more confused and it makes it worse.
Well, they're fucking handwriting.
Well, that too. So,
That'd be me.
well, okay, so 11. So I'm looking at this, I'm like, okay, I'm trying to get to sine times tangent squared. Right now I've got tangent minus sine. So I don't get anything on my sheet where I've got tangent squared minus sine squared. So I'm looking at that for a minute, and I'm like, okay, let's see. What else can I do with this? Okay, let's try that. I see tangent squared, and I'm like, I don't want to mess with secant, so let's do this. Let's do sine squared of x over cosine squared of x. Because any of my trig identities, remember, we keep saying you can use exponent rules, because some of you are like, I don't see that anywhere on my sheet. If I square everything that's involved here, I still have the exact same thing. And that's why I said I'm not going to write every single identity, but understanding that I can manipulate this is something that could come in handy. So doing this would be perfectly legal. So I get to here, and I go, okay, I would need a common denominator. And I'm starting to look at this, and I'm going, am I getting myself into trouble? Well, let's find out. Because sometimes we may find out what we tried the first time doesn't work. But let's see if this works. What's my common denominator going to be? Okay, cosine squared x. And don't forget, whatever I have originally in each of my fractions is still going to be there. Okay, so let's see. Do I need anything in my first fraction? No, because I've already got cosine squared x. I'm just going to leave that alone. What about my second fraction? Yeah, what do I need there? Okay, I need a cosine. So let's see what this looks like. Holy cow, this is looking ugly. Okay. Let's see here. I still see that minus. Now that's got me a little concerned here. Hey, I have an idea. Now I can't cancel because for me to be able to cancel, I'd have to be able to cancel it out. We got this blasted bond here. But I have a different question for you. Do these two things have anything in common? What does sine squared x and sine squared x cosine squared x have in common? They both have a sine squared x. So, they're like, Hardy, we're going to run out of room. I see this. We're taking this a little bit in a roundabout way, but we're going to get there. So if I factor out sine squared x, I get 1 minus
Oh, I see. I got it.
because I swear we're thinking on this one to get there. Okay. So I start looking at this, and I'm like, okay, what else can I do? What else can I do? What else can I do?
Turn sine x squared and cosine x squared to rectangle.
Say that again?
Okay, well, 1 minus cosine squared is just sine x squared. Sine squared.
Okay, now, but here's my question with that. If I turn that back into sine squared x, am I going to end up back where I started here? Yeah.
But doesn't sine squared x and cosine squared x turn into tangent?
Yeah, but now where's the sine squared x going to come from?
It's out of the box. Oh, the minus 1 minus cosine. Right.
They're like, Hardy, you're starting to drive us
1
crazy.
1 minus cosine squared is sine squared.
Yeah.
I said that.
Wait. Wouldn't it turn from tangent x squared plus, or no, times the sine of x squared?
Say that one more time.
Wouldn't cosine squared and the cosine squared, would that turn into tangent squared?
Yes.
And then the 1 minus cosine squared would turn back into sine squared?
Okay. I agree with about 3/4 of what you just said, and we're close. Because what you just mentioned was you're like, well, can I take this part and do what I kind of want with? But here's the one dilemma you have.
That's going to be the wrong order.
Well, it's not the order, because you could change these. They're interchangeable as far as order goes. But here's the dilemma that you're going to run into. If I just tried to deal with this part,
Yeah.
I see what you're saying. We can get away with this.
Yeah.
Because if I take this,
That turns into
there's my tangent squared of x,
and 1 minus
and 1 minus cosine. I'll go with you on that.
Yes.
Is there an easier way to do this?
As far as simplifying shorter steps on this one, not that I can see.
Alright. Is there one like this?
No, there is not one that crazy. You know how I am. I like throwing these on reviews and worksheets to get you to think, but then when it comes down to it, I normally don't do that same thing when it comes to those. So, speaking of identities, though, before some of you go into total shutdown here, is there anything from here we need to chat about? Or, yeah, I was going to say, or if any of you need note cards, I'll stick them on top of the projector here so you can get situated with that, too. The quiz preview? Nope. Number 6. Let me come up here.
Yeah, good choice, Priscilla Presley.
All right. Let's see what we got working here. We got cosecant squared times tangent squared minus 1 equals tangent squared. All right, let's see what we got here. So cosecant squared would be 1 over sine squared. What's tangent squared minus 1? Is that going to help me with anything?
Yes.
Kind of?
Yeah.
How does something kind of help us?
Because it's possible.
Because it's possible. Well, yeah, they're all possible. The question is, do we get there?
Yeah, dude.
Yeah, so can I do something with tangent squared minus 1? There's just this daze that goes about us. They're like, Hardy, here we go again. Oh, you guys. Okay, what could I turn tangent squared into? Okay. I'm just going to rewrite this, keep reminding myself. Okay. Okay, do you see where I've just changed tangent squared into this and secant squared into this? Are we okay so far with that? Okay, now, these are being multiplied. Can I cancel anything?
Sine squared.
Okay,
Sine squared.
those are being multiplied, I can cancel. Yeah, this isn't a minus bond with these two, I'm multiplying, so I can cancel that. So I've got 1 minus cosine squared minus 1. What's 1 over cosine squared
Secant.
going to be? It's going to be secant squared. And secant squared minus 1. It's the details. That's the wonderful thing about trig. For those of you that are not detail oriented, this is like a good training course in detail orientation. Again, the minus is what kind of locks us in. At first we were looking at it as tangent squared minus 1 has to be something. Then we didn't see that. Then we went to the back. Well, what can I do with tangent? You've got to keep running through the process of, if this doesn't work, try this. If this doesn't work, try this. You can't just say, my first thing didn't work, screw it, I don't get it. That doesn't work.
Are you going to get your school today?
Yes,
Okay, can I come in?
absolutely.
Okay, cool.
We got time for number 7.
We have time for number 7. Okay, let's do this. All right, secant squared. What's secant squared equal if I just want to keep it in a fractional form like this here? Okay, so got 1 over cosine squared. Now what's secant squared minus 1 again? Anybody?
Wait, what are we doing?
Okay, tangent squared. You're like, okay, that's not helping me yet. It will.
Turn that into sine of cosine.
Yeah. Now that I've got this into tangent squared, I want this turned into sine and cosine stuff. So tangent squared would be sine squared over cosine squared.
Then you flip it.
Then we go flipping.
Then you cross out.
So I'm like, okay, I leave the numerator alone, and I flip this guy. Cosine squared over sine squared. Now that all the minuses and stuff's gone, now I can free cancel, which is 1 over sine squared, which is cosecant squared. Yay!
Did you do one?
I can.
Can you?
1. Party going a million miles an hour on 1. Watch, see how fast my mouth can move.
Hey, everyone. Bye.
Something like
Otherwise,
that.
I can come after school and we can do it.
That's fine too, because, oh yeah, we're going to have a time issue. Okay.